get started for second part of chapter 9. Okay, last time we talked about what are proteins and how protein is constructed by individual amino acids, and we call the linkage peptide bonds. Okay, we call linkage peptide bonds. And we also showed the structures of proteins. That is basically a linear chain of amino acid with a backbone and with the R groups on the side, if you guys remember the picture shown before. So today we're going to talk about first types of proteins, and then we'll focus on how that chain of amino acid folds into a functional protein. We can talk about the structures of proteins. And then the last part, we're going to talk about the hydrolysis of protein and also the denature of protein. So let's take a look at the composition of protein and what are protein made of. Okay, proteins can be classified into two types. Okay, one type, which is not that common, called simple proteins, contains only the amino acid polymer, the chain of amino acid. That's it. The one we have seen before, actually, in the first part of the chapter, are simple proteins. They are basically a polymer of amino acid, a chain of amino acids, making a polymer. But most proteins, especially protein that carries a function, are conjugated proteins. That means besides the amino acid polymer part, the chain of amino acid part, it has other components, either organic or inorganic components, conjugated together. This word conjugate means what? Means linked together. Okay, linked together. So besides the amino acid polymer, it's conjugating with some other components, either organic or inorganic. And the other components of proteins are called prosthetic groups. And depends on the type of prosthetic groups. Again, what are prosthetic groups? Then other components, either organic or inorganic components. Depends on those prosthetic groups, we can further classify conjugated protein into these types. These are very commonly seen major types of conjugated proteins. And this is the table. I think you can find it from above. Okay, for example, hemoprotein. Okay, hemoprotein means the protein is conjugated to a organic molecule called the heme. Okay, we're going to show the structure next page. What does the heme look like? It's an organic structure, heme. And here in the center of the heme is an iron. Okay, actually has an iron in it. Okay, lipoprotein means what? Protein conjugated with lipid. Remember we studied in lipid chapter? Cholesterols are transported in our bloodstream with what? In the form of what? Lipoprotein. We have LDL, HDL means what? High density lipoprotein. Low density what? Lipoprotein. Some are good cholesterol, some are bad cholesterol. And those are lipoproteins. Okay, glycoprotein. Glyco, this prefix means what? Carbohydrates, means the proteins are conjugated with carbohydrates, such as our antibodies. Okay, antibodies are carbohydrate, are basically glycoproteins. Phosphoprotein means protein has what? Some phosphates. Okay, some phosphate actually acting as a switch, turning on and off the protein function sometimes. Later on, see some proteins. Okay, phosphate groups sometimes serves as a switch for a channel, for example. Okay, nuclear protein means what? Protein conjugated with nucleic acid. Okay, if you guys know, if you study microbiology, you will know that virus is a structure of what? Protein shell with what? Nucleic acid inside. Basically, a virus is a piece of nucleoprotein. Okay, and metalloprotein means what? Protein conjugated with metals. Okay, so you can see that these are conjugated proteins. Basically, it's polymer of amino acid conjugating with these small organic or inorganic prosthetic groups. Okay, like we said earlier, see, this is a few examples of conjugated protein I want to show you. Okay, you can see the ribbons. Okay, the ribbons with different colors, ribbons, tubes, whatever, are the amino acid polymer part. And you can see that each protein is conjugated with this purple structure, that purple structure is shown here. This is called a heme. Okay, heme. And the center of the heme is an iron. Okay, this is a structure of a hemoprotein, actually hemoglobin. Okay, hemoglobin. Hemoglobin is with the main protein molecules on the surface of our red blood cell, responsible for transporting what? Transporting oxygen and carbon dioxide. Okay, if you breathe, oxygen is breathed into your lung, through your lung, into your bloodstream. The oxygen is actually tightly bound where? Here, at the heme. You can see that do you see that tiny, these two double ball? That's an oxygen. Okay, of course, in the form of O negative. It's actually bound with the iron metal at the center of the heme. Okay, without that heme, this protein will not carry oxygen or carbon dioxide. Okay, so this is one example showing what is a conjugate means. Protein conjugating with what? Some other components, prostatic groups. Okay, this picture is a picture of our antibody. Okay, because antibody, this is the typical antibody structure, has two long chains and two short chains. Okay, they're heavily glycosylated on the heavy chains of the antibodies. Okay, glycosylated means what? Conjugate with carbohydrates. Okay, this is a picture of, this is a picture of lipoprotein. You can see that on the outside they're protein and also lipid bilayers, and the cholesterols are hidden inside to be transported. Okay, you can see that the proteins are like islands, icebergs, inserted on the lipid bilayers. Okay, this is a conjugation of lipids and proteins called lipoproteins. So these are a few examples showing you what are conjugated proteins. Proteins conjugating with what? With other components. Okay, other components. Can be small components, can be major components. You can see lipoprotein, the most part of it seems to be lipids. Okay, but they're conjugate proteins. Does it make sense? All right, now, no matter what type of protein, okay, either conjugated or simple protein, they have a functional protein part, the polymer part. But if you guys remember, we said earlier in part 1 of this lecture, proteins are basically a chain of what? Amino acid, right? Like you're making a line. You can, like you're waiting for a movie or buying something. You're like one person at a time, you're making a line. No branches, no matter how long the line will be, you will never make a branch, right? When you wake up waiting for a movie, you may be several lines, but you can always be in the same line. So that means a chain of amino acid has to do some kind of folding eventually to become a what? A protein, a functional protein. Remember, protein is a 3-dimensional structure. And most of our proteins are kind of spherical. Okay, we call it globular protein. The geometry, the shape of the protein mostly are spherical. Some proteins are maybe fiber-like, like our hair proteins. Okay, keratin, they're mostly fiber look. But most proteins are like these. But these proteins, remember, if you pull it straight, if you could imagine, it will be what? Will be a chain. Like your necklace will be a straight chain, no branches, one bead. Each bead represent what? One amino acid. So from here, a line, a chain, straight, to here, to a functional protein, there must be what? A lot of folding. You have to fold, fold, fold. Eventually, like your cat playing with a like a thread, right? Eventually, they're gonna fold into a what? Into a fur ball or something. Okay, protein does the same thing. So we're gonna learn today, how does this chain of amino acid becomes a functional protein? And of course, eventually it will conjugate with some protein group as well. But we want to learn how does this structure becomes possible. And that involves 4 levels of structures. Okay, 4 levels of structure. We call those 4 levels, very simple, primary, secondary, tertiary, and quaternary structures. So let's take a look. What are these 4 levels? Okay, what are these 4 levels? And again, 4 levels. Okay, 4 levels from the chain all the way fold to a what? To a protein. Okay, these are the 4 levels. Again, we're going to talk about all 4 of them. The first level of protein structure, primary structure. It's very simple. Not folding yet. Is the sequence of the amino acid in the protein. What is sequence? Sequence means what? Which person is first one? Who stays after him? Who is the third person? The exact sequence of these amino acids is called the primary structure of the protein. Remember, the sequence of amino acid we normally know is written from what? From N-terminal to C-terminal. Okay, C-terminal. And that sequence is called the primary structure. Okay, sequence is very important because the sequence of the amino acid, the first one until all the way to the last one, determines the following structure, determines how this chain is going to what? Going to fold. Okay, I want to show you a very simple example to show why the sequence is important. Take a look at these two amino acids. Only two amino acids, glycine and alanine. When they make a peptide bond, they make a dipeptide, like only two amino acids, not even a chain. Okay, there are two ways of doing that. One way, the first one on the N-terminal is what? It's glycine. You can see, take a look at the bottom chain. Still these two amino acids, alanine and glycine, but they switched. So the chain now is on the first amino acid is what? Is alanine. The second one is what? Glycine. Do you see that? Only two amino acids. You can arrange it in two ways. A, B, and what? BA. Does it make sense? And of course, these two will have totally different biological functions if they are biologically active. So that sequence is, again, the primary structure. That determines all the further subsequent structures. Does it make sense? That's called the primary, the first level of protein structure. That is the foundation of the following levels of structures. Okay? With that, let's take a look. What is secondary structure? Secondary structure. Secondary structure is the three-dimensional form of local segments. Okay, three-dimensional form of local segments. Okay, local segments. Okay, three-dimensional, you guys can understand what is three-dimensional in a 3D format. But what is local? Take a look. This is a protein. May not be a real, or may not be a real protein. But if you take a look at this protein, okay, take a look at this protein. Some part of the protein is like the what? Like this ribbon, right? You see there's a ribbon here, ribbon here. Some part of the protein is what? Like the band, right? These are called local. Okay, this whole thing is the whole protein, but this piece is called a local segment. That piece is called a local segment. These are all local segments. And these local segment structures are called secondary structure. Secondary structure. There are mainly two types of secondary structure, or two forms of secondary structures commonly seen in the protein. One is called the alpha helix. Alpha, you can use the Greek letter alpha as well. You don't have to write down the word alpha. Another one is called the beta pleated sheet or beta sheet. Now, guys, based on the name, alpha helix and the beta sheet, can you take a look? Can you tell me which one do you think is the beta alpha helix, which are beta sheets?
The blue one is the alpha.
The blue one are what?
The blue one is the alpha helix and the green one is the...
Blue one is alpha helix, the green ones are what? Beta sheets. Exactly what's the means. That's how we represent a protein. When you have a picture of a protein in a 3D like this, that's how we show the alpha helix and the beta sheets. And you know now they're what? They're a local, right? They're not whole piece of protein. They're just some local pieces folded initially to give you some local fragments. Okay, give some local fragments. So let's take a look. What is alpha helix and what is beta sheets? And most importantly, when you have an alpha helix or you have a beta sheets, what forces are used for making them holding up together? Like remember, you have alpha helix. Think about if you use a rope or a thread, like knitting thread, can you make an alpha helix? You cannot, right? Because once you make it, the alpha helix is going to what? collapse, right? There's no way it can hold that tight so that, oh, your piece of rope can hold it into an alpha helix structure. Unless you use a copper wire or something, they're rigid, right? Can you imagine that? The same thing, we want to ask, hey, if you have a stable alpha helix, what are the interaction forces, chemical forces, holding these pieces stable so that you can maintain the alpha helix or the beta sheet structures? So let's take a look. What are the forces? The forces for all secondary structures, including alpha helix and the beta sheets, coming from the backbone. Okay, coming from the backbone. And if you take a look at the backbone, what we studied in the first part of the chapter, and let's take a look at the backbone again. The backbone of a protein is what? Alpha carbon, peptide bond. You see that? Alpha carbon, what? Peptide bond. Alpha carbon, peptide, alpha carbon. It's always repeating like this. This is the backbone. And we know these are what? The side chains of each alpha carbon. And we know the peptide bond. Okay, peptide bond is basically a what? An amide bond, right? What is an amide bond? C-O-N. On the end there's a hydrogen. C-O what? N. C-O-N. It's all what's the peptide bond, what bond is. Okay, peptide bond. So because of the peptide bond and because of the backbone has a lot of peptide bonds. Okay, if you have 100 amino acids, you have 99 peptide bonds. If you have 10 amino acids, there's 9 peptides. There's a lot of them in the backbone. So because of the peptide bond, also it has CO and N. So there's a possibility of the oxygen of the peptide bond can interact with the hydrogen with another peptide bond at a further distance. When they interact, they will give you the secondary structure. Okay, when they're secondary. You can see that the hydrogen bonding between the carbonyl oxygen and the amino acid of another peptide linkage further along. Okay, further along. What does it mean further along? Think about it. Take a look at this one and this one, for example. Hydrogen, this is the hydrogen on this peptide. This is the oxygen on the other peptide. If we have a line, these two can never what? Interact, right? Because they're too far. But think about secondary structure is what? 3D structure. What 3D means? These two, if they're standing in the line, they can be further away, but these two can what? Can fold. Is that right? Think about it, you have a rope. One spot on if I pull a rope, a string, one on my left hand, one on my right hand. These two spots are further, right? If I put my string. But if I fold the rope, what happens? These two stops can what? Get close to each other. The same idea, if the peptide is a chain, if they fold some way, then there's a chance the oxygen on one peptide bond can interact with the hydrogen, what? Further away along the chain, along the backbone. And that gives us the supporting force of all secondary structures. Again, what is the supporting force? I put in bold. Is what? The hydrogen bonding of what? Of the backbone. And to be more specific, hydrogen bonding of what? Of the peptide. Okay, of the peptide bonds. Okay, take a look what I mean about hydrogen bonding and alpha helix. Okay, this is the picture showing you what does the alpha helix look like. Again, helix, you guys know, is what? It's like a coil. Okay, this is like a coil. And this picture shows you the hydrogen bonding. You guys see that? The oxygen interact with what? The hydrogen. The oxygen and interact with what? Hydrogen. But because it's folded, so this C, O actually originally is actually what? Further along the chain of what? Of the backbone. But because it's folded like a coil, these two can have a chance to what? To interact. Does it make sense? Take a look. This guy is here. The other guy is there. If you pull it straight, they're going to be further away. But because it's coiling up, so the O of one peptide can interact with what? With the H of another peptide further along the backbone. How further, we're gonna see later, next page, how further normally for alpha helix. Okay, cannot be like extremely far. And there's a pattern, nature designed this. Okay, as you can see, the hydrogen bond is a lot of them. Okay, because every O, there's gonna be one guy that is further along can interact with back. So every O, there's another one. So you can see that how many hydrogen bonds are there? A lot of them. You see the dashed lines? They're all hydrogen bondings. And because of the hydrogen bonding, what happened? The coil can stay what? Very stable. They will not collapse. Not like your rope. It will stay very stable. Okay, very stable. Okay, this is the model of alpha helix. Okay, this is the model of alpha helix. And this is the top view of the alpha helix. Okay, very interesting. What do you see? When you see that, when you view from the top, like my eyes are here from the top, what do you see? This is what? The helix, right? There's a hole inside, of course, there's a coil. But these are what? What are the green ones? The R groups, the side chains. They're all what? They're all outside the coil. Okay, they're all outside the coil. So there's a lot of R groups outside, and that will be responsible for our next level of structure. Okay, because they're outside, they're exposed. Okay, again, this is the 3D view of the alpha helix. Okay, alpha helix. Does it make sense, guys? Okay, here are a few facts about alpha helix. Okay, the twist of the helix is right-handed. Okay, again, these are nature design these molecules. They're clockwise or right-handed. The hydrogen bond between the CO and AH is parallel to the axis of the coil. You can see that it's always like a straight to the axis of the coil. Okay, the purple, these dashes represent hydrogen bondings, a lot of them, but they're all what? All parallel to the axis of the helix. A given hydrogen bonding involves a CO of one amino acid and the NH of another amino acid approximately 4 residues away. Okay, to be more specific, it's around 3.6 residues. Okay, you may see how further, around 3.6 amino acid away. When you fold back, see that? They will interact. Okay, not very far, 4 residues away. Okay, 4 residues away. So that means whoever interacting with the C or O, they're what? There are 4 amino acids residue between them. And again, like I pointed out in the last picture, the R groups extended what? Outwards of the spiral of the helix. Okay, there's nothing room inside, they're always outside. Again, there is a reason for that. Okay, these R groups outside will be responsible for later, for what? For tertiary structures. Right? This is alpha helix. Let's take a look at beta sheets. Okay, beta sheets. Beta sheets is another type of secondary structure. Means what? The interactions are also because of the hydrogen bonding of what? Of the amide bonds, of the backbone. But instead of coiling, instead of making a spiral, beta sheets making turns. You can see that this is what a beta sheet look like. The amino acid are making U-turns. Okay, the chain is making U-turns. So when you make a U-turn, what happens is the O of one chain is going to interact with what? With the H of another chain, because you're making U-turns. So when you make U-turn, you can see that the O of one part piece is going to interact with the H of another piece. So there's a lot of U-turns, a lot of hydrogen bondings between these turns. Okay, between these turns. And when you make a lot of U-turns, you make a what structure? Like a planar sheet structure. Planar structure. That's called beta sheets. Okay, beta sheets. Okay, this is what I mean, U-turns, like this. When you make the U-turn, you get what? You get it like a planar sheeted structure. Okay, but the interaction is still what? The hydrogen bonding of O and what? And N. Okay, I'm sorry, and NH, and the H on the end. Okay, because again, they're folded back. They can interact between these two folds. Okay, between these folds. Okay, this is another picture showing you the beta sheets. Okay, and the hydrogen bonding between the CO and AH are within the plane of the sheet. This is the beta sheet. You can see them make a U-turn, make a sheet, and you can see the hydrogen bonding are where? Within the plane. If this were come up, unless this is the sheet, they're within the plane. But if you take a look at this model, the green ones, the side chains are where? Are outside the plane, either on top of the sheet or what? Below the sheet. So they're still exposed to what? Outside, not within the structure. They're actually exposed to outwards. Again, for what purpose? For our next level of tertiary structure purpose. Tertiary structure. This is again the beta sheet. You can see that make turns, and then the R structures are outside. Does it make sense, guys? Tertiary structures. Okay, again, very important. No matter alpha helix or beta sheets, what forces are responsible for holding these structures together? The hydrogen bonding of what? Of the backbone. Okay, what is backbone? Alpha carbon, amide. Alpha carbon, amide. So basically, it's the hydrogen bonding of these what? Of these amide bonds on the backbone. Nothing to do with the R group. The R groups are now exposed outside for what? For next level of structures. Does it make sense, guys? All right. Here's a picture of again, maybe a hypothetical protein. Besides alpha helix and beta sheets, okay, besides alpha helix, beta sheets, there are maybe some components joining these secondary structures called unstructured segments, or called random coil. Okay, that's pieces of protein that connecting these secondary structures together. Okay, and these are called, again, unstructured segments, or sometimes called them random coil. Okay, these are some random coils. You can see that. Okay, alpha helix, what? Beta sheets. Again, the lines here showing you what? The hydrogen bonding. Because of this hydrogen bonding, you can have a stable what? Coil structure, or what? A plated sheet structure. Remember, if you want to hold a string, you cannot hold it into a beautiful coil. Why? Because you don't have the supporting force for that stable structure. You guys see that? Secondary structure, right? Easy? Okay, I know you need a lot of like a 3D in your mind, but I'm trying to give you a lot of picture to give you that idea about how amazing nature is from a chain to give you something like this. Okay, next. Okay, next. Again, this is our second, this is another picture showing you the secondary structure. This is a real protein. I took it from maybe a protein database. You can see that these are alpha helix, and these are what? Take a look here. Beta sheets, and between them there's some random coils, unstructured segments joining them together. Okay, you cannot all have alpha helix or beta sheet, otherwise your protein is going to be too rigid. Does it make sense? You need these random parts holding these structures together so your protein can what? Can be alive, can be flexible to be a functional protein. Okay. Plating proteins are like our machines in our living systems. They need to work. And these random coil guarantee that the proteins are what? Are flexible, okay, not a rigid structure. Now, after primary structure, we know it's a sequence. Secondary structure is the local segment. After that, this local segment will further fold. Like this is I'm using a phone line to show you what a further fold means. Let's say this is a secondary structure, an alpha helix. But the alpha helix, the whole secondary structure can further what? Fold again. Okay, like folding like this. This is the coil, and then the coil further fold to give you like a more 3D structure. Now, if it further fold means what? There are gonna be some forces joining this part and that part together so that your phone line can look like this. And that forces here, interaction here, holding these two together like a glue. You have to put a glue there so that this doesn't separate. And that glue, that interaction is what we're going to talk about, tertiary structure. But we know the backbone of the chain is already used to make secondary structure. So the only thing that can interact between there and there will be what? Will be the R group. Remember we said the R group, no matter alpha helix or beta sheets, are where? On the outside. So they're perfectly outside. Hey, I'm here, let's interact. And when they interact, you get what? A tertiary structure. So what is a tertiary structure? Tertiary structure is basically a pair of R groups interacting together. Of course, there are a lot of pairs in one protein, but each tertiary structure, each tertiary interaction is a pair of what? R group. So how many R groups are we talking about? 2 R groups. They interact, they contribute to one tertiary interaction. Again, guys, take a look at this picture. It's a very nice way to tell me what is tertiary. In order for, here for example, I'm folding this back. In order for whatever this amino acid interact with this amino acid, in order to them interact, you need some what? Some pin or glue. What is glue? The R here and the R here can what? Interact. So that means between this spot, there are 2 R groups for whatever way interacting with each other. Why? Because R groups are outside, remember. Alpha helix, where is R group? R groups are where? Are all outside. Okay, perfectly for tertiary structure. So let's take a look. Okay, let's take a look. How many types of tertiary interactions we could have? Okay, how many types of tertiary interactions can contribute to the real tertiary structure of a protein? Now, in order to understand this tertiary interaction, we have to review one topic we learned in the beginning of this class, the classification of amino acid. Remember we said amino acid can be classified by their what? By their side chains. Remember that? We know amino acids all look the same, right? Except what? The side chain is different. And because of the side chain different, we classify amino acid into how many types? 4. What are they? Polar, neutral polar, neutral non-polar, and basic, which is polar, and acidic. Very good, these 4 types. Okay, because of these 4 types, take a look at these interactions. If your side chains are both non-polar, you see hydrocarbon, hydrocarbon, they will like each other because they're non-polar. Again, we said tertiary is how many side chains? 2 side chains. Okay, only 2. Each tertiary is only 2 side chains. If they're both non-polar, they like each other, we call that interaction hydrophobic interactions. So what is hydrophobic interaction? It's the interaction between 2 what? Non-polar side chains. Okay, here's another hydrophobic. You see that? 2 both non-polar. This is the benzene ring. That is a hydrocarbon. Again, they're both hydrophobic. Why? Because they're non-polar. Next. If you have 2 sulfur side chains, remember there's only one amino acid that has what? SH, that is cysteine. Remember that? We see that earlier in the part of the chapter. If you have 2 sulfur on the side chain, then these 2 sulfur can make a what? Covalent bond linkage. We call this linkage disulfide linkage. This is a very unique tertiary structure. It has to involve 2 identical amino acids, cysteine. If that's the case, then we'll make a covalent bonded tertiary structure. That is only one type of covalent bonded tertiary structure. Only one tertiary structure that is covalent bonded is this guy. Disulfide linkage. Next, if you have 2 polar amino acids, like the OH, like the amide, then the H and the O will interact with each other through hydrogen bonding. Okay, this hydrogen bonding now is a tertiary structure. What is the difference between this hydrogen bonding and what we just saw, the hydrogen bonding here? This is the secondary structure, right? What is the difference between this and this? They're both hydrogen bonding. Why this is called tertiary? That's called secondary.
That's because it is outside the chain.
Outside the chain?
No, outside the backbone.
Outside the what? The backbone. Very good. The secondary structure, the hydrogen bonding is because of what? The backbone, the amide bonds, right? This hydrogen bonding is because of the interaction of what? These two are what?
R groups.
Side chains or R groups, remember. That's the biggest difference. Secondary structure, these hydrogen bonding is because of the backbone, the amides. Everybody has it. But this is a pair of what? Side chain. So they're both hydrogen bonding, but they're coming from different parts of the protein. Does it make sense? Secondary come from what? The backbone amide. Tertiary come from what? Two polar side chains. Okay, two polar side chains. Does it make sense, guys? Okay? Last, if you have acidic side chain and a basic side chain, then the acid will transfer a hydrogen to the base, so you can have a positive and negative interaction. We call this interaction electrostatic interaction or salt bridge. There are two ways of both the same. Okay, sometimes they call it a salt bridge or electrostatic interaction. Electro means what? Positive and negative. How can you get a positive and negative? Acid side chain and what? Base side chain. So the acid can give a protein to the proton to the base. You get a negative and what? COO minus and NH3 plus. Again, these are side chains. Okay, you can put a note here. Sometimes your book or somewhere is very common. They're both very common. Electrostatic interaction or salt bridge. It's kind of like I make a bridge. They're all salt. Okay, you can pick and do it. And when you answer the question, you can do either way. But if it's multiple choice, you have to know salt bridge is what? Electrostatic interaction. So here, this picture shows you how many types of tertiary interactions? 4 types. Electrostatic interaction, hydrophobic, disulfide, and hydrogen bonding. 4 types. Okay, 4 types. Does it make sense, guys? I think you have this picture in your book, right? Do you? No?
Yes, we do.
You do? Maybe
46,
different.
Page 46.
Okay, yeah, maybe different arranged.
Oh, yeah.
Yeah, we did.
Yeah,
Sorry.
yeah, I don't need it, you don't need it. You can take a picture, of course, but I think you have it is maybe better. Right, so let's take a look at a few examples. I want to go over details. Okay, this one is the easiest one. Okay, for us to study wise, the easiest one. Okay, is what? Disulfide linkage. Do you see that? 2 what? Cysteine. Again, you can see these 2 cysteine are not even in the same chain, but spatially they're close to each other. They can make a what? They can make a disulfide bridge. Okay, these 2 are not close, but when the structure folds, you can see that they make a linkage. Or you can understand when they make a linkage, these 2 are what? Bring together. Okay, this is the contribution of tertiary structure. What does it mean, tertiary structure? And here we're actually looking at 2 chains, but these can still make a bridge. Okay, that's called tertiary structure because they're in interaction of what? The side chains. Okay, these are the structures of the polar groups. Okay, the polar groups could be acid or basic group, or it could be OH and amide group. As long as they're polar, there's a possibility of what? Hydrogen bonding. Okay, polar side chains, you will have hydrogen bonding. And remember we said earlier, when we classify amino acid and base side chains are also what? Polar. So when they have another polar group, they can have hydrogen bonding as well. Okay, there's a possibility. We don't know. We don't study all individual proteins, but when we look at these groups, there's a chance they will have what? Tertiary hydrogen bonding interaction. Okay, again, and more facts about hydrophobic interactions is in water solutions, okay, where proteins are in a water environment. Many proteins have their polar R groups outwards, even interacting with water. And their non-polar R groups will be what? Will be hidden inside, okay, interacting with each other. Okay, that's called hydrophobic interactions. And compared with other tertiary interactions, hydrophobic interactions are weak, are relatively weak. But in a protein chain, normally we have a lot of hydrophobic amino acid. So the number of hydrophobic interactions are what? Are great. So the magnitude of hydrophobic interaction is still very important for the structure of protein. But if you look at a single one, hydrophobic interaction is the weakest. But you have a great number. Okay, remember, if you look at the amino acid classification, most of the amino acids are what? Non-polar amino acids. So hydrophobic interaction has a we call cumulative effect because there are too many of them. So overall, they are still very strong interactions giving the structure of a protein. So now you guys know that after secondary and primary and tertiary structures, we have a what? We have a protein will look like a certain way. And of course, why your protein can look like this is determined by what? The sequence. Okay, the protein, whatever the protein will look like is already preset when you have a what? Have a chain made, when you have a sequence of amino acid chain. That's called the primary, secondary, and tertiary structures. Okay, make sure you know what are they and why what the interaction is what we're talking. What interaction means what? Something is interacting with somebody, and you have to know what is it. Okay, be able to name these interactions. Okay, and finally, quaternary structures. Okay, all proteins must have primary, secondary, and tertiary structures, but not necessarily will have quaternary structure. Quaternary protein exists when a protein have multiple chains or multiple units. Remember, a protein is what? Is a chain amino acid. If a protein has multiple chains, then they will give multiple units. And those multiple units, in order to hold together to make a protein, that interaction is quaternary structures. Okay, but not all proteins have quaternary again. Okay, it is only found in this is the word called the multimeric proteins. What is a multimeric? Multimeric means proteins that are multimeric have what? Have two or more peptide chains. We call them units, subunits. Each unit is actually independent from each other, but they can bind together to make a what? Make a protein. And that binding is called quaternary structures. Okay, again, this is the example of what we have seen before. This is the hemoglobin. It's a very beautiful quaternary structure. It actually contains 4 units. Okay, 2 units called alpha chain, 2 units are called beta chain. They're identical, like 2 pairs of units. They're held together. If you want to know what held them together, it's mainly hydrophobic interactions. Okay, between one chain and another chain, they have hydrophobic interactions across the chains. And that hold quaternary structures together. Again, it's not universal on all proteins. Some proteins don't have quaternary structure, but some proteins do. Especially those proteins with complex biological functions. Okay, I have a picture here showing you the beautiful quaternary structures. Okay, you can see these quaternary structures have different sizes. Involving this one, for example, only have 2 units. This one has 3 units, 4 units, 5, 6, 7, 8, 9, 10. And this one has what? A lot of units stacking together to make a channel. You can see that it's like a channel. This is the ion channel or something other channel. I just want to show you, amazing, again, how nature designed these biomolecules. Okay, these are all quaternary structures. And again, you can see that protein, you can see primary, secondary, and tertiary. You cannot see primary, but you can see secondary and tertiary interactions. Does this make sense, guys? right? And this is again the summary of what we have showed. Maybe I turn out the lights, you can see better. Okay, the 4 levels of protein structures. Okay, 4 levels of protein structures. The primary structure, again, is what? The sequence. Secondary structure mainly involves alpha helix and beta sheets. It's held by what? By the hydrogen bonding of where? Of the backbone of the amide bond. And after you have the secondary structure, you can see the side chains are where? And the outside, either outside the coil or top or bottom of what? Of the plane, of the beta sheet. And because they're exposed outside, they can have what? Tertiary interactions. So your proteins can further fold. And the tertiary interaction is because of what? Because of these side chains. A pair of side chain contributes to 1 tertiary interaction. And then if you have 2 units, you got a what? Quaternary structure, but not universal. Some protein only have up to tertiary interaction. All right, so that's structures of proteins. Does it make sense, guys? All right, let's move on. We have 2 small topics, and then we're done. Okay, first small topic is protein is a large molecule, right? But when we take a protein in, for example, eat some beef, meat, pork meat, beans, we have to what? We have to digest them, right? We have to put them back to the building blocks. So that process is called protein hydrolysis. Okay, it's the same reaction what we do in the lab or in our digestive system. We're doing hydrolysis reaction. What hydrolysis? Cleave the amide bond. Okay, but protein hydrolysis, okay, it's nothing like you're chopping off a necklace, taking 1 bead at a time. It's a little different. Usually protein hydrolysis happened internally. Like you don't chop from the one person on the top first. You chop off what? In the middle. So a large chain of protein becomes what? Small segments, small pieces, small peptides. Because those some enzymes can selectively chop off a peptide bond between. So your large protein becomes what? Smaller ones. And then your smaller ones can further hydrolyze into what? Into a pool of amino acids. What do we mean pool? Because a protein is made by what? A lot of amino acids. So protein diet eventually will become a what? A huge library of what? Of individual amino acids for us to what? To make our own protein. Okay, for us. Usually amino acid doesn't provide energy. It does. If it does, it's very minimal. Usually amino acid taxene is either make our own protein, or sometimes amino acid can transfer into some other nitrogen containing compounds. Okay, for example, if you guys remember when we study chapter 6, we have some small molecules hormones, right? Dopamine, epinephrine, norepinephrine. They're actually coming from amino acids. Okay, depends on type. Some amino acids does convert it to other molecules because they contain nitrogens. Does it make sense? This is called protein hydrolysis. Of course, this process needs a lot of enzymes, mostly digestive enzymes, so that the reaction can happen in a very mild condition in our physiological conditions. But if you were to hydrolyze a protein, or mostly a peptide in the lab, you need extreme conditions. Peptides bond are very stable, just like we studied in chapter 6. Amide bonds are what? Very stable. So if you want to hydrolyze a peptide, for example, this is a dipeptide, 2 amino acids. If you want to hydrolyze this peptide in lab, you have to use extreme conditions. What extreme means you need heat and either acid or base. If you guys remember, we have actually seen this reaction before in chapter 6. When you hydrolyze an amide bond, first you need to look for what? The amide bond. What is the amide bond? C-O-N. Right? This is the amide bond. This is only one amide bond because you have only 2 amino acids. See that? Alpha carbon, amide, alpha carbon. That's it. N terminal, C terminal. When you hydrolyze the amide bond, the CO becomes what? COH, right? NH becomes what? NH2. That's how you got hydrolyzed. But, like I said, in order for the reaction to move forward, you have to either use acid or base. If you use acid, the NH2 will not be NH2. NH2 will be what? NH3 plus. So both of the amino acid NH2 will be NH3 what? Plus. Does it make sense? How do we get NH3 plus? Because NH2 will take a what? Hydrogen plus from the acid. Does it make sense? If you use base, COOH will not be COOH. Will be what? CO minus Na plus. CO minus Na plus. Remember, now you have 2 of them because each one has a COH, each one has an NH. Do you understand both reactions? You will see them in your quiz and test. Okay, let's practice based on this. You guys have this picture, right? Do you have this scheme? Mm-hmm. All right, if you have that, then you can refer to that. Show me the products of this reaction. Okay, this is under acidic condition. Okay, work on your. Do you have that in your notes? You do? Okay, it's covered. Good. So I don't accidentally give you. Okay, work on them. This is a tripeptide. Okay, I even put colors for you. Okay, put colors for it. So this is a tripeptide means what? You have 3 products. You have 3 products. Okay, don't worry. I think in your tests and quizzes, I won't give you more than tripeptides. It's not worth it. I mean, as long as you know the concepts, you can do 2 dipeptide or tripeptide. Good enough. You don't have to worry about like 10 amino acids or 5. It's not worth the time. Okay, so take a look. Under acidic condition, what do you get for this tripeptide hydrolysis? Put on board. Right, this is the tripeptide. Okay, try to work on them. First, copy it, of course, like we did before. You didn't? Okay, we can work together after that, but try it. Use that scheme. plus here, so it will be what? NH3 plus.
So all the hydrogen can be added here.
Correct. As long as there's nitrogen, you have to add a hydrogen plus because they're all bases. Remember we said under acidic condition. Let's just go back.
Oh, so 3 times.
Correct. See, under acidic condition, all the NH will become what? NH2 plus. Alright, guys, take a look. Let's work on this together. Like I said, no matter it's a disaccharide or I'm sorry, dipeptide or tripeptide. Okay, the first thing, this is what? Protein hydrolysis. Hydrolysis means cleave what? Amide bond. So you have to first, again, this is the basic of the first part of the chapter. You have to, when you look at a piece of peptide, you have to identify first how many residues and what? How many peptide bonds. And where is the peptide bond? You have to first be able to identify. We even practice that in the first part of the chapter. So when you look at the structure, that one is even color coded. But if you're without color, okay, when you look at a piece of peptide, you have to first identify where's the backbone, right? Backbone is what? N-terminal, alpha carbon, peptide. Alpha carbon, peptide. Alpha carbon, C-terminal. So that means what? You only have how many peptides? 2 peptides. If you 2 peptides, you have how many residues? 3 residues. And also you can sell by how many alpha carbons? Alpha carbon, and what? Alpha carbon. Sorry, I missed a hydrogen here. Okay, that's how you identify a piece of peptide. Again, that's the basic requirement for this chapter. Okay, the one I need to identify in the test as well. You will see that, both in your third test, in your quiz, and also in the final. Now, after you identify the peptide, you can mark it. Okay, because now we're doing hydrolysis, so I'm marking this is the peptide bond, CON. Is that right? And this is what? Another peptide bond, CON. And we know hydrolysis, so I need to do what? I need to cleave it. So I use my eraser, cleave the peptide bond. After cleave the peptide, I need to what? Add water, because that's what? Hydrolysis. So I add OH to the acid, OH to the acid, H to the what? To the N. OH to the acid, H to the N. So NH now here also becomes what? Becomes NH2. Is that right? You add a hydrogen. Where's the hydrogen from? From water. Again, we're doing hydrolysis. What is hydrolysis? Adding water. You are adding 2 water because you have 2 amide bonds.
So what about the first one, the H3N plus?
That's already H3 plus. You don't need to worry about that. That's given. Again, depends on what you're given. Good? And then I said, in order for the reaction to move forward, this is just hypothetical step. In order for the reaction to move forward, we need either acid or what? Or the base. This reaction is under acidic condition. Means what? Means all the bases will be converted to a salt. What is the base? The N. So how do we convert N to a base? NH2 becomes what? NH3 plus. NH3 becomes what? NH3 plus. That's it. The acid, you don't touch them anymore. COH, COH, COH. Does it make sense? So the products are, let me draw it here, CH, COOH, CH3, NH3 plus. This is one of them. Second one, COOH, NH3 plus. This is the second one. This is glycine. And the third one, NH3 plus, CHCOOH, CH2SH. This is the third one. Okay, all 3 have COH, but NH2 will become what? NH3 plus. Because you have what? Acid. Okay, first take a look. Under acidic condition, NH3 becomes what? You see that? NH3 plus and COH. R1, R2, again, you copy. You won't miss anything R. There's nothing to do with R in this case. Okay, another part to refer to, I'll turn back to the one we studied in first part of this chapter. Take a look here. When you hydrolyze under acidic condition, see that? Adding acid, here is adding acid. NH3 becomes what? NH2 becomes what? NH3 plus, and COH is still COH. This is how an amino acid will exist under what? Acidic condition, under low pH. Is that the same? COH, all COH. NH becomes what? NH3 plus. Does it make sense, guys? Okay, this is our, again, these are all the reactions we didn't know about chapter 11. Okay, you got 3 products. Again, 1, 2, and 3. All 3 products, the same format. COH and what? NH3 plus. And of course, if it is under basic condition, NH3 plus won't be NH3 plus. Will be what? Will be NH2, but COH will be converted to COO minus. You don't even need this Na plus, it's fine, as long as this one is negative charge. Okay, you won't have NH3 plus because under basic condition, the proton will be what? Taken away. Think about that way. Now hydrogen plus will be taken away by what? By that guy. So you only have a negative charge because the hydrogen plus is gone, it's taken away. Okay, so that's protein hydrolysis. Again, this is showing the reaction under different pH, what products you will get. And they apply for the same thing. It's the only difference is, again, under us, our physiological condition, the condition is milder. Okay, we don't need to worry about adding acid or base because we have enzymes. Okay, but our products will still be like this because our physiological condition is not neutral. So some amino acid will exist as O minus, some amino will exist as an Na plus. Depends on their isoelectric point. Okay. Right, that's protein hydrolysis. And final topic, a few minutes will be done, is a very unique feature of biomolecules, including proteins, and later on nucleic acid can also have this reaction. Not reaction, chemical change. We call that denature. Okay, denature or denaturation, I guess. Okay, you can just call it denature. Okay, what is denature? Denature is a process in which a protein, again, in chapter 11, nucleic acid will do the same thing. Is the structure of these biomolecules, and for protein, of course, the structure of proteins are lost. But for protein, not all structures will be lost. Remember we said protein structures of what? 4 levels, right? Primary, secondary, tertiary, and quaternary. In denature process, secondary, tertiary, and quaternary structure will be lost because of some extreme condition for that protein, of course. But the primary structure will be remained. Now, if you think of what is the primary structure? What is the primary? The sequence, right? So that means what? After denature, the protein is still a what? A chain. And that chain is going to tangle with each other because you no longer have nature-made beautiful secondary tertiary structure. The chain will be like again, your cat playing with a leaning thread. will randomly coil with each other to give you what? Give you like a fur ball or thread ball. And your protein will no longer be soluble in water, will no longer have its nature state. Your protein will be more like a aggregate or precipitate, like a solid. And that process is called denature. Take a look at this. This is the protein, very beautifully folded, have secondary, tertiary, and quaternary structures. But after denature, all these secondary, tertiary is gone. You only have a what? Like a coiled, tangled thread. And your protein will look like this. This is the sunny side up, right? Don't worry about the yolk. Your protein is like this. Aggregated solid. That's why we eat egg white. Before denature, your egg white is beautifully folded protein. They can be soluble in water. If you put your egg white in water, it will be soluble. But after you cook it, your egg white will no longer soluble in water. Why? Because what you're eating is what? Denatured egg white proteins. Does it make sense, guys? Okay, that's called, again, denature. Okay, your protein is still a protein. It's just no longer a what? A folded functional protein. Okay, you still have a chain of protein. Okay, that's a very important difference. And that's the difference between denature versus hydrolysis. What do we get from hydrolysis? Amino acid. Your chain is even gone. Denature is different. Denature of protein is still what? It's a protein. It's just no longer the original one. Okay, no longer original. Okay, this picture also shows you denature use paper clips. Okay, so this is the quaternary structure, 3 units. After denature, this is what you got. The clips are wired, tangled together with nothing. It's just like aggregated protein. Okay, and finally, this table shows you what conditions cause protein to denature. Okay, the condition could either be physical condition or chemical conditions. Okay, all these conditions will cause or potentially cause protein to denature. And you have to know these conditions. You don't have to memorize them all, but you have to at least know a few. If people ask you, or if you experience something, hey, will that cause protein or denature? Okay, including heat, of course we're cooking, right? Cooking is basically we denature what? Raw protein. Microwave, UV, these radiations will cause protein to denature. Whipping, right? You guys, if baked, you know if you whip, like heavy whipping the egg white, well, what would you see? It becomes what? Like a foam, right? That's the same, denatured. Whipping, mechanical whipping. Detergent, you wash hands. Is basically you denature what? Bacteria or virus proteins. That's why detergent works on killing back microorganisms. Okay, organic solvents, ethanol, propanol, acetone, these will denature protein as well. Strong acid and bases, heavy metals, and some reducing agents. So these are some chemical and physical conditions that will cause denature, and of course you can read if you're interested. What modes is their function to denature these proteins? All right, that is all for chapter 9. Okay, can we close the